Alright, I wanted to go through some problems I got some interest in here. Practice 5.1c solutions, and let's jump into that. The first problem says, by reference to the movement of charge in a metal and in a plastic, explain the electrical properties of conductors and insulators. So let's talk about that. Well, in an insulator, you have a bunch of atoms that make up an insulator, and they are kind of trapped in some kind of a structure, and in each one of those atoms there is a central nucleus that is positive, and around the outside there are negative charges that are carried by particles called electrons. And so inside of an insulator, all of these electrons are bound tightly to their atoms. And so there is no net charge in each atom. Each atom has a net charge of 0, and the electrons are unable to move between atoms. However, in a metal, what happens is that there are some electrons called valence electrons that are mobile. That is to say that, for the most part, each one of these atoms might give up one electron into a sea of electrons that's free to move around inside the metal. So most of the electrons are bound to their atoms. However, inside of a metal, each atom drops one electron into this free electron pool and becomes a positive ion. So a metal is really made up of these positive ions that are in some kind of a structure, and a sea of negative electrons that are free to move about inside of this positive ion lattice, right? So these free electrons, if there's no net charge or no potential difference between the two ends of this wire, the free electrons just bounce around randomly and bump into these ions and start heading the other direction or whatever. And so they just randomly bounce around. Right, so a metal conductor has positive charges that are fixed, and some of the electrons are mobile, and those are called free electrons. Right. Whereas a plastic insulator has positive charges and electrons that are all fixed. Number 2. In a copper wire, the number of conduction electrons equals the number of copper atoms in the wire. Alright, so I'm just going to write down some notes here as I'm reading. And I would write that one like this, that there's a relationship that for every one atom, there is one conduction or free electron. All right. It says, state what is meant by conduction electrons. And we just kind of covered this. These are valence, or they are free electrons that are not bound to any one particular atom in the metal. They're loosely bound, and inside the metal, those electrons can flow from one atom to another and bounce around between these positive ions. B says, the density of copper is 8.93 times 10 to the third kilogram for each cubic meter, and its molar mass is 64 grams. Deduce that the number of moles in copper, a volume of 1 meter cubed of copper, is 1.4 times 10 to the 5th moles. All right, let's jump into that. This is really a problem around conversion. And so I'd like to set up the way that I convert and say, we want to say that the number of moles in a volume of this much copper is equal to something. So we're going to start with that volume, a volume of 1.0 times 10 to the third. I'm sorry, 1.0 cubic meters of copper. So 1.0 cubic meters of copper. And we want to convert this using a series of fractions that are all equal to 1. All right. I want to go from a volume in cubic meters and eventually into moles. And they give me several numbers that'll help me out along the way. One of them is this density of copper, 8.93 times 10 to the third kilograms for each cubic meter, or per cubic meter. All right, so I'm going to write that down here. I think that might help me out. We have 8.93 times 10 to the third kilograms is equal to 1 cubic meter of copper. All right. If I want to put half of this equality on the top and half of it on the bottom of my fraction so that I have the top and the bottom are equal, and I want to cancel out this cubic meter, I'm going to put this side on the bottom. So I'm going to have from these green boxes, I guess, I'm going to have 1 cubic meter. I'm going to put that side on the bottom. And then on the top, I'm going to have 8.93 times 10 to the third kilograms. So right now, if I'm looking at my progress here, I could cancel out these units on the top with these units on the bottom. If I have meters cubed on the top and meters cubed on the bottom, they'll cancel out. And right now I'd be in units of only kilograms. So I've gone from a volume, now I'm in a mass. And next, I want to get towards moles. Well, they give me a relationship here that says its molar mass, the molar mass of copper is 64 grams. And you likely remember from chemistry that that means this. That means that if 64 grams is the molar mass, then 64 grams is equal to 1 mole. That's what a molar mass means. All right, so if I knew if I could get into grams on the top, then I could cancel out and get into moles. Well, I know how to get into grams. I can find a relationship between kilograms and grams pretty easily because in my data booklet I have a little table like this that tells me that kilo just stands for 10 to the third. And that is to say that if I write 1 kilogram, it's the same thing as replacing this kilo with times 10 to the third. So I can write 1 kilogram is equal to 1 times 10 to the third grams. All right, this means kilo. Good, so now I have another 2 boxes here. I have 1 kilogram and 1 times 10 to the third grams, and those two things are equal. And I'm going to use those to cancel out kilograms. So I have kilograms on top. I'm going to want the kilograms part of that, the 1 kilogram on the bottom, and I'm going to put 1 times 10 to the third grams on top. And now, if you're following along here, kilograms and kilograms, I'll be able to cancel. Right now I'd be in grams. I don't want to end there. You see I have this relationship between grams and moles, and so I want to use that next. This grams can cancel with this side of the equation that has grams here, the side of the equality, I guess I should say, and the other side 1 mole. And now if I was to multiply all these fractions, I would end up with an answer in moles, and that's what I want. I want an answer in moles. So let's go to it. I have 1 times 8.93 times 10 to the third times 10 to the third. That's 8.93 times 10 to the sixth. I have on top moles, and on the bottom I have 1 times 1 times 1 times 64. And so if I calculate that out, I will get for myself 1.4 about times 10 to the 5th moles, rounded to two significant figures here. All right. Excellent. Let's move on. 2B2 says estimate the number of conduction electrons in 1 cubic meter of copper. All right. Well, we just found the number of moles in 1 cubic meter of copper, but now they're saying how many conduction, how many free electrons would be in 1 cubic meter. I mean, that's a lot of copper. That's a 1 meter by 1 meter by 1 meter tall. How many electrons would be in this? Well, we have a relationship up here that says this. It says that for each atom in this block of copper, there is 1 conduction electron. So if we can get from moles to atoms, then we could get from atoms to conduction electrons, and that's what we're going to do. So we'll start out with 1.4 times 10 to the 5th moles. We need a relationship between moles and atoms, and Avogadro gave us that. He said that 1 mole, no matter what it is, in this case it's copper, but doesn't matter, 1 mole is always equal to Avogadro's number, which is in your data booklet in the constants, is equal to 6.02 times 10 to the 23rd atoms. All right, and this will let me cancel moles and moles. And now that we know, now we would have how many atoms there are, and we have this relationship that says for every 1 atom, we have 1 conduction electron. That's not to say how many electrons we have, because there's a lot more electrons than that, but the rest of them are bound around their atoms, and just 1 for each atom is released into this pool of electrons that can swim around between these what are now positive ions. All right, so this lets us cancel atoms and atoms, and we have 1.4 times 10 to the 5th times Avogadro's number on top over 1. That's going to give us, well, it's like 8.4 times 10 to the 28. We have conduction electrons here. So that's 8.4 times 10 to the 28 conduction electrons. Here we go. Moving on. 2C says, the diagram below shows some of the conduction electrons in a copper wire. The arrows represent the random velocities of the electrons. Explain by reference to the motion of the electrons why there is no current in the wire. All right. Well, current means that there would be a net charge moving one way or the other. That is what current is. And so what we could do is we could look at these velocities of the arrows and see if, even though some of them might be going this way, are most of the electrons traveling one way or the other, right? So this one is going to the right, and this one is kind of going to the right. Here's to the right. This one's kind of going to the right, and then to the right. And then, geez, it seems like about just as many of them are going to the left here. It looks to be about equal numbers going to the right and to the left. And so if there's no net motion in any direction, that is to say, on average, most of them are going this way or this way. That doesn't mean every one of them. If there's no net motion of electrons, then there's no transfer of charge. There's no transfer of charge one direction or the other. And that means that on an average, as much charge is moving to the right as there is moving to the left. So there is no current. So let's let's record some of those ideas here. So we said there's no net motion of electrons in any direction, and therefore, I like to write this, but that means therefore, there's no transfer of charge. That means that there's as much charge moving left as right, and therefore there is no current. Excellent. Moving on. It says an electric field is established inside the copper wire directed as shown in the diagram. The dots represent electrons. The random velocities of the electrons are not shown in this case. On the diagram, draw an arrow to indicate the direction of the drift velocity of the electrons. All right, so just like if this was a board and those were little marbles and we tilted the board slightly, what establishing an electric field does is it causes each one of these electrons to feel a push in a direction that is somewhat interesting here. Here's what we got. If we have an electric field, this electric field is defined as the direction that a small positive test charge would be pushed. All right? So electric fields point towards a positive charge. I'm sorry, electric fields point towards a negative charge and away from a positive charge. Well, how about an electron? If we have an electron here, if an electric field shows the direction that a positive charge would be pushed, that is to say that we must have something, a bunch of positive over here maybe, and a bunch of negative over here. Well, our electron, he loathes negative charges. He wants to get away from those, and he would like to head over here to this group of positive charges. So the direction our electron would be pushed is actually the exact opposite as the electric field. And this stems back to Ben Franklin, who, America here, who said that positive charges are current. The flow of positive charge is what current is defined as. And so now that we know that current is really made up of these negative charges, that means that even though current is to the left in this case with the electric field, that the flow of electrons would be to the right. All right. Next up, I think this is 2D. An electric field is established inside the copper wire directed as shown in the diagram below. The dots were, 2E. A typical value for the electron drift velocity in copper wire is 10 to the negative third meters per second. In the circuit below, the length of copper wire joining the negative terminal to the lamp is 0.5 meters. The switch is closed. Calculate the time it would take for an electron to move from the negative terminal of the battery to the lamp. All right. Well, this is stems back all the way to our early days, and here's our lamp. All right. And they tell us that if this distance is 0.5 meters and we're traveling a velocity, so distance is equal to 0.5 meters, we're traveling a velocity equal to 10 to the negative third meters per second. Isn't that crazy? You think of electricity as moving so quickly, But it's not true that the electrons move very quickly. They move so slowly. Look at this, on the order of a millimeter each second. That's really slow. All right. How long is this going to take us? Well, you know, if we have velocity is equal to distance divided by time kind of thing, therefore time is equal to distance divided by velocity, and we have a distance here of 0.5 meters and a velocity of 10 to the negative third meters per second, and we end up with like 1.5 times 10 to the 2 seconds. No. Hold on. Next up. Oh man. That's not 1.5 times 10 to the 2. That's 5 times 10 to the 2 seconds. All right, that makes more sense. Okay, next on our sheet we have says the lamp lights in a time much less than that calculated in E1. Explain this observation. If you've ever flipped a light on, you know that this is true, that the light lights almost instantly. How could this be true if the electrons really are moving that slowly? And the answer is this, that that inside of the wires, just like if you were to turn on the faucet in your kitchen, the water is flowing almost immediately, even though the source of water is very, very far away. Well, the reason for that is because there's already water in all of the pipes leading up to, you know, it's not like screwing in a hose and turning on the water and then you have to wait for the water to go all the way through an empty hose. That's not the situation. So inside of all the copper wires or all of the metal wires, there are already free electrons just banging around, and they are there already. And so what flipping the switch really does is it sets up an electric field in the wire, and that happens very, very, very quickly. And so the inside of the light, you know, you have your inside of the light, you have this wire already that's got, and this is just part of your circuit here. And inside of the light, there's already all of these negative charges, these negative electrons. There is no current until you flip the switch. There are just as many negative electrons traveling to the right as to the left. Like we saw before, that means there's no current. But they are all just banging around inside of this wire. As soon as you flip the switch, all of the electrons feel a push in one direction in the wire, and so they begin to march. Now, that doesn't mean that they're just traveling in a straight line. Like, you know, if this is one electron inside my wire, it doesn't just, you know, just start marching in one direction, because there also inside my wire is all of these positive ions. And what happens is that the electrons, they try to head in one direction, but they're banging into positive ions frequently. And so what ends up happening is the path of the electron looks more like they bang around, but on average, they are all headed one direction. All right. Finally, number 3. describe the concept of drift velocity as applied to the conduction electrons in a conductor? All right, well, what this drift velocity represents then is that these electrons, they are accelerated by the electric field set up in your wire. So here's my wire, here's all my positive ions. Those positive ions are locked in place, right? They're part of the lattice of, all right, so there's all these positive positive ions of metal that have given up one electron to the flood of electrons that are all heading around. As soon as I set up an electric field, that is to say that as soon as there's an electric field inside the wire, well, I'm going to change my electric field and run it this direction. Make for a better picture here. All right, so as soon as I set up an electric field inside of this wire, let's say it's heading this direction, then my electron is going to feel a push, just like if my electron was a marble and I lifted up this side of and created some kind of a ramp here with a bunch of pegs in the board, right? My electron would keep banging into pegs, but essentially it would be traveling down the board. Over time, the pegs would just slow it down. Well, these conduction electrons have high random speeds when they're accelerated by an electric field inside of a conductor. And although they collide frequently with these lattice ions, they obtain a net speed in the direction opposite to the field. So if the field is traveling, if the field is directed this way, the electrons, they might bang around, and sometimes they might even go backwards, but essentially they maintain a net velocity that is traveling in the opposite direction. So this would be the drift velocity, or the direction of the drift velocity. Essentially, they all drift in the same direction, and that's why there's a current in the wires, because there is a transfer of charge. All right, well, that's the end of that practice. Please let me know if there are more questions. I'll be glad to help out as much as I can.